Hello students, we're continuing with Newton's laws, and now we're going to look at Newton's laws as applied to connected objects. So here's a typical connected object problem. I've got a tow truck pulling a chain connected to a car of mass m1, and then there's another chain which is pulling mass m2, another car. And the question is, what is the acceleration going to be? We're going to assume there's no friction, and we're going to assume that the car's wheels have no inertia. And you might be wondering, well, what are we talking about here? And this has to do with something that's going to come up later in the course. And yeah, what's the acceleration? So there are two ways to do this problem, and I'm calling them the easy way and the hard way. But the hard way is something that we still want to be aware of and make an attempt to understand, because it's going to come up. The technique is going to come up in the future. But anyway, let's first focus on the easy way. So the technique is real simple. What you're going to do is combine these two things here, cars 1 and 2, masses 1 and 2, and say, well, this is just like one big object, and it'll have mass capital M. And so, okay, if you do that, it simplifies the problem. The acceleration is just going to be the force from the pickup truck, or the tension on this rope, the same thing, right? And divided by the mass of this big system that is, that's the two cars put together. And okay, so capital M was just M1 plus M2, and so we get the answer. The acceleration is the pulling force of the truck, or if you want, the tension in this chain, divided by mass 1 plus mass 2. So there you go. That is the answer. Now, I have here a little reminder. I do need you to open the book, right? Because just knowing the easy way is not enough. I need you to read this section. Okay. Now, here comes some explanations from, basically, I'm explaining it the same way as the book, just, my style. So here we go, the hard way. So the first step is going to be to draw free body diagrams. Now, the tension here, T, is the pull of the rope. So right here, the tension T is pulling, to the left on mass 1, and the tension T is pulling to the right on mass 2. So if I go back here, the tension T is pulling to the left on mass 1, and the tension T is pulling to the right on mass 2. Going back to mass 1, here's the pull of the pickup truck. All right. So now that we've got this, we're going to apply Newton's second law to each of these things. So looking at mass 1 first. So we're going to say the net force acting on mass 1 is going to be the mass times the acceleration, right? So Newton's second law is F equals ma, right? And F is really the net force. Okay, so we've got the net force 1 is equal to mass 1 times A. And for M2, we have net force 2 equals mass 2 times A. Okay, now we're going to arrange things a little bit. So the net force on mass 1, right, is the force to the right, and I need to get rid of this 1 here. I should have erased that. Anyway, it's pulling to the right, so this is positive force, and minus the tension, and the tension's pulling to the left. So the tension takes away from the force, the pulling force. And so this here is the net force, and so that's mass 1 times A. The net force for mass 2 is just the tension, so we've got the tension is mass 2 times A. Now comes a algebra trick. In algebra, it's okay to do just about anything as long as you do it equally to the stuff on the right side of the equal signs and to the stuff on the left of the equal signs. So you can take the square root of both sides, you can add to both sides, you can subtract to both sides, you can do anything as long as you do it equally. So here what we're doing is we're adding these two equations. So we're going to add the stuff here on the right hand side, and it gets us m1a plus m2a. Okay, so we added the stuff on the right hand side. Now we're going to do the same with the stuff on the left hand side. So we're going to have f minus t, that's this right here, plus t. Right? And so we did the same thing on the left side and on the right side. We can do that. That's what algebra says. Okay. So now that we've done that trick, we're going to simplify. And so now you've got, well, the t's cancel. So you've just got left with the force, the pulling force from the pickup truck, equals, here I I factored out the a, so I've got m1 plus m2 times a. And now I've divided both sides by m1 plus m2, and I get f over m1 plus m2, which is the same answer as we got the easy way. Okay, so the hard way isn't really that hard, but what makes it a little bit odd or feel strange is that it's not something that you would think of naturally. It's not obvious. It's not hard, but it's not obvious either. And so anyway. Okay, now putting in some numbers, just, to see how things work here. Let's suppose the truck was pulling with 2,500 newtons. Suppose that car 1 had a mass of 1,500 kilograms and car 2 its mass was 2,000 kilograms. What would be the acceleration? And so, okay, you can just plug in the numbers. Here's the pulling force. Here's mass 1 plus mass 2, and you get the answer. All right. So now I'd like to work a little bit on the question of why do we want to learn how to do it the hard way? And the answer is because sometimes you can't just combine the inertias, right? So here, what made it possible to do it the easy way is that we could, just combine mass 1 and mass 2 to get a combination mass, and it worked. But sometimes you can't actually do that. And so, for example, let's suppose that the wheels of the two cars had some rotational inertia. So this is something you're going to learn about later. Then the easy way is no longer an option. You have to do it the hard way. Okay, so enough of that one. Let's do another really typical problem. So in this problem, you've got mass 1 hanging from a rope. This rope goes over a pulley. The tension here in this rope is redirected, and it pulls mass 2, which could be a car with wheels with no friction and no inertia. And the analysis is exactly the same. You get the same answer, F over the combined mass, mass 1 plus M2. Now, what's interesting in this particular case is that the force is the weight of mass 1. So it's mass 1 times gravity. And so okay, so anyway, that's the answer. I guess what makes it kind of interesting is that you could rewrite this like this. You could say it's G. The answer is just G times this factor M1 over M1 plus M2. So, that's another way of looking at it, which is kind of interesting. Now, this particular problem brings up something that is kind of interesting and fun and useful to do in physics, and that is the technique of thinking about limiting cases. This is something that you really need to start doing as you get into your career in physics. And so real physicists, think about limiting cases all the time. This is a very nice trick or technique to help you get rid of the wrong answers. So limiting case 1. What if mass 1 were really small? Let's say it was just a feather. What would be the acceleration then? And I think you can figure out the answer. And the other limiting case is, what if mass 1 was, tremendously huge, much bigger than mass 2? What would the acceleration be then? And what you can do is you can go back a couple pages, and in the left margin in this area to the left, there's the answer. And finally, one last question. This is not a limiting case question. What if the pulley here had mass? Right? So you had mass 1, mass 2, and the pulley's mass. What would you do then? And the answer to that is in Chapter 11, and it's example 11-7. And you'll see that the analysis there, it follows the same techniques as the quote-unquote hard way that we did before. And that's why it matters. That's why you kind of want to be able to do this sort of algebra. There's more stuff in the chapter. There's homework problems and so on. I need you to look at the book, do the homework, and yeah. So thank you for watching. Bye-bye.